Today we're starting on a section called Types of Waves. So here we'll be looking at how we can classify different sorts of waves and some of the differences between them. So it turns out that for any wave, we can use a few criteria to sort of split them into different groups. So one thing that we can look at is the direction of vibrations of the particles in the wave. It turns out that for water waves, the ripples will cause the water to vibrate up and down, but for some other sorts of waves, this isn't the case. So we'll be looking at that a bit later. The other way that we can differentiate between waves is by looking at the medium through which the wave propagates. So we'll be looking at different sorts of waves, the way that particles move in them, and the medium that they travel through. So first of all, let's look at the direction of vibration. It turns out that particles in a medium can behave in two basic ways, right? They can vibrate in a direction parallel to the wave's motion, which we can see on the top here. So we can see that the rings of the slinky are moving in the same direction as the wave is propagating. Or they can vibrate in a direction perpendicular to the wave's motion. So in this case, we can look at the bottom picture. We can see that the rings of the slinky are moving up and down, despite the fact that the wave is traveling in the other direction. So when we're moving up and down like this, then we say that the particles are moving in a direction transverse to the wave's motion. That means that we can call these transverse waves. So some media, such as gases, for example, can't actually transmit mechanical transverse waves because the gas particles are simply not connected to each other. We can't get a gas particle moving up or down, getting the gas particle next to it to also move up or down. For a slinky, we are able to do this. If one part of the slinky moves up, then it will pull the next part of the slinky up, and so the wave will propagate. Electromagnetic waves happen to be a form of transverse wave, because if we shake an electron in one direction, then the wave will propagate perpendicular to the direction that we're shaking the electron. So when a medium vibrates parallel to the wave's motion, then we say that it's a longitudinal wave, right? And so we can see that in the example of the slinky. The parts of the slinky carrying the wave are vibrating in the same direction as the wave is traveling. And we can see that that will allow the wave to propagate through the slinky. So sound waves are a type of longitudinal wave because for sound waves, the air particles which are carrying the wave vibrate in the same direction that the sound wave is traveling. So sound is able to propagate through solids or liquids or gases. If we have a sound wave trying to propagate through a gas, then the gas will vibrate in one direction, and that means that it will collide with gas particles next to it. And so in that way, the wave can propagate through the gas. Now, if we look at waves propagating through a medium, they'll be being transferred by mechanical waves most of the time. So what is a mechanical wave? It turns out that adjacent particles can influence each other through contact forces. So for a longitudinal wave through a solid or a liquid or a gas, this influence is simply the particles colliding with each other. So if a gas particle is vibrating left and right, then it will bump the particles to the left and right of it, and that will cause the disturbance to propagate through the gas. If we look at a wave on a string over here, we can see that the tension forces between each section of the string are what are causing the string to go up and down and cause the wave to travel across. So we can see the forces on each part of the string over here. So each part of the string, or each particle of the gas, will push or pull on its neighbors, and by exerting this minor force on their neighbors, they'll cause the disturbance, the wave, to propagate through the medium. Now it's possible to transmit a wave using other forces instead of contact forces. If we shake an electron at one side of the room, then we generate an electromagnetic disturbance. And this electromagnetic disturbance will propagate without using contact forces between the electrons. Instead, it will be using electromagnetic forces. So this is a different sort of wave. It's not a longitudinal wave, and it's not a mechanical wave because it doesn't use contact forces. It is in fact a transverse electromagnetic wave. And so if we look at the electromagnetic fields created, we can see the electric field in white and the magnetic field in blue. So we can see that if the wave is traveling from left to right, both the electric field and the magnetic field are perpendicular to the direction of motion, and therefore it's a transverse wave and not a longitudinal wave. Now, aside from light, we have some other forms of electromagnetic wave which don't rely on contact forces to travel. So, aside from light, we have radio waves, microwaves, which are used to cook food inside a microwave oven, infrared and ultraviolet light, X-rays, and gamma radiation. So all of these are very different forms of wave, but they're all electromagnetic waves. So going from top to bottom, this goes from in fact the lowest energy wave to the highest energy wave. So radio waves will have less energy in general than infrared and ultraviolet light, and of course visible light is sandwiched right in the middle of these. And gamma radiation will have far more energy than any of these other forms of electromagnetic radiation. However, they are all electromagnetic radiation, and so they're all caused in the same way, and they all propagate in the same way. And now it turns out they don't actually need electrons to propagate. They can propagate just through having the electric and magnetic fields. And because of this, they can travel through a place even if there are no electrons. This means that they're propagating through a vacuum. Another form of wave that can, in theory, propagate through a vacuum is a gravity wave. There is one small problem with this though. We haven't discovered them. In theory, gravity waves are produced by rapidly moving or vibrating masses. This would cause a gravity wave to travel through space without a medium. The problem is, although we've detected that they probably should exist, we've never yet observed one, so we can't say for sure that they do exist. Now, mechanical waves, so waves that cannot travel through vacuums, include things like seismic waves in earthquakes, sound waves in air, and water waves. Now, these waves require energy to be passed between different particles, whether it's particles of rock, air, or water. So in this case, they can't travel through a vacuum. They need a medium, which may be a very different medium, in order to travel. Right, so that's the end of the theory. We've looked at how to classify different sorts of waves and the differences between transverse and longitudinal waves and mechanical and electromagnetic waves. So let's go on to some questions.